Welcome to this deep dive. You sent over Andriy Burkov's The 100-Page Machine Learning book.
Oh, yeah, it's a really great resource.
Seems like a fantastic way to get a solid grasp on machine learning.
Definitely.
So we're going to unpack each chapter,
Okay.
highlighting those key concepts and connecting them to real-world applications.
Sounds good.
So you can really see how all this stuff actually plays out.
Absolutely. What I find fascinating about this book is how it covers so much ground without getting too bogged down in all the complexity.
Yeah,
It's a really great starting point
for sure.
for anyone who wants to, kind of demystify machine learning.
Okay, so chapter 1
Yeah.
jumps right into the big question. What is machine learning?
Right?
But before we even get to a definition,
Yeah.
Burkov tackles this common misconception about machines actually learning.
Yeah, he uses this interesting analogy of a video game where the screen suddenly gets rotated.
Okay.
And he points out that a human player would probably adapt pretty quickly. But a typical machine learning algorithm would be totally lost unless it was specifically trained to handle rotations.
So it's not really learning in the same way that humans do.
Right. It's more about recognizing patterns
Yeah.
and making predictions based on data.
And Burkov even points out the
Yeah.
kind of marketing savviness behind the term machine learning.
Oh, absolutely.
Right. Like back in the 1960s,
Yeah.
IBM needed this catchy phrase to attract clients and talent.
Yeah, machine learning definitely had that futuristic ring to it,
Yeah.
even if it wasn't like a perfect description.
Right. So there's a bit of history behind the hype.
For sure.
But now let's get to the actual definition.
Yeah.
How does Burkov define machine learning?
He defines it as a field of study that gives computers the ability to learn without being explicitly programmed.
Okay.
So basically, instead of programming a computer with specific rules for every situation, we feed it data and let it figure out the rules itself.
That's pretty amazing when you think about it.
Yeah.
Instead of programming a computer to recognize a cat,
Right.
we can show it thousands of cat pictures
Yeah.
and let it learn the features of a cat on its own.
Exactly.
Okay, so chapter 2
Okay.
dives into the math behind machine learning.
Right. The essential math.
And Burkov doesn't assume you're a math whiz.
No, not at all.
He breaks down those core concepts
Yeah.
like scalars, vectors, and matrices,
Yeah, the building blocks.
which are really the building blocks for understanding these algorithms.
Exactly.
I remember struggling with vectors and matrices in school.
Oh, yeah.
Can you give us a quick refresher
Sure.
on what they are and why they're so important?
So think of a scalar as just a single number,
Okay.
like the temperature outside.
Got
A
it.
vector is like a list of numbers,
Okay.
kind of like coordinates on a map.
Uh-huh.
And a matrix is like a grid of numbers, like a spreadsheet.
I see. That's it.
And these concepts are crucial because they allow us to represent and manipulate data in a way that computers can understand.
Okay, that makes sense.
Yeah.
So, for example, if we're trying to predict housing prices,
Right.
each house could be represented by a vector
Yeah.
containing features like size, number of bedrooms, and location.
Precisely.
And then a whole bunch of houses could be represented by a matrix.
Exactly. And then Burkov also explains other essential mathematical tools like summation, product notation, and functions.
Okay.
These are all important for understanding how algorithms work and how we optimize them.
Optimization. That sounds like we'll be hearing a lot about that.
Oh, yeah, definitely.
Can you give us a sneak peek at what that means in machine learning?
Well, think of it like trying to find the best settings for a camera
Okay.
to take the perfect picture.
Okay.
In machine learning, optimization is about finding the best parameters for our algorithms to make the most accurate predictions.
Got it. And that often involves using calculus concepts like derivatives.
Derivatives, now we're really going back to school.
Yeah.
Can you remind us what derivatives are?
So remember, derivatives tell us how a function changes as its input changes in machine learning.
Yeah.
We use derivatives to figure out how to adjust the parameters of our algorithms to reduce errors and improve predictions.
Okay, so
It's like using a compass to guide us towards the optimal solution.
Oh, okay. That's starting to make sense. But math isn't the only foundation we need for machine learning.
Right.
Burkov also delves into
Yeah.
some key concepts from probability and statistics.
Absolutely. So chapter 2 also covers concepts like random variables,
Okay.
probability density functions, Bayes' rule,
I've heard that one a lot.
and maximum likelihood estimation.
Okay.
These are all essential for understanding how algorithms deal with uncertainty
Okay.
and make probabilistic predictions.
Bayes' rule. Can you remind us what that's all about? Sure. Bayes' rule is all about updating our beliefs based on new evidence. Right. It's like saying, okay, I thought this was true, but now I have new information, so I need to adjust my belief.
Got it.
In machine learning, we use Bayes' rule to refine our models as they encounter more data.
So it's like our algorithms are constantly learning.
Exactly.
And improving their predictions based on new information.
Precisely. So now that we've laid the mathematical groundwork, Chapter 3 dives into the different types of machine learning.
Okay.
He introduces supervised, unsupervised, semi-supervised, and reinforcement learning.
Oh, yeah. I've heard those terms before.
Yeah.
Always get them mixed up.
Okay. Well, imagine you're teaching a child.
Okay.
To distinguish between apples and oranges.
Okay.
In supervised learning, you'd show them labeled examples of apples and oranges.
Okay.
And let them learn the distinguishing features.
So in supervised learning, we provide the algorithm with labeled data, meaning we tell it what each example represents.
Exactly.
Okay, got it.
Now imagine you give the child a basket of fruit without any labels.
Okay.
In unsupervised learning.
Yeah.
The child has to figure out how to group the fruit based on similarities and differences.
Okay.
Without any guidance.
So unsupervised learning is all about finding patterns in data.
Right.
Without explicit labels.
Right.
What about semi-supervised learning?
Semi-supervised learning is a mix of both.
Okay.
Imagine you label a few apples and oranges, but the rest of the fruit is unlabeled.
Good.
The child can use the labeled examples to get a head start, and then try to label the rest based on what they've learned.
Interesting. So it's like combining the best of both worlds.
Exactly.
What about reinforcement learning?
Reinforcement learning is like teaching a dog new tricks.
Okay.
You give the dog rewards for good behavior.
Okay.
And penalties for bad behavior.
I got it.
And the dog learns to maximize its rewards over time.
So it's all about learning through trial and error.
Exactly.
And feedback.
Exactly. But for this deep dive, we'll be focusing primarily on supervised learning.
Okay, sounds good.
Which is the most common type and the one that Burkov delves into the most.
Okay, so let's dive into the world of supervised learning.
Right.
Chapter 3.1 introduces the concept of a hypothesis. And a loss function, which sound pretty technical.
Yeah, they do.
Can you break those down for us?
Sure. So imagine you're trying to predict housing prices.
Okay.
Your hypothesis is basically your model's guess about the relationship between the features of a house, like size and location, and its price.
So it's like a mathematical formula that predicts the price based on those characteristics.
Exactly. And the loss function measures how good or bad your model's prediction is. It tells you how much your prediction deviates from the actual price.
So the lower the loss, the better the model.
Precisely. And Chapter 3.2 introduces two types of supervised learning problems.
Okay.
Classification and regression.
Okay, those sound familiar.
Yeah.
Can you remind us what they are?
Think of classification, like sorting emails into spam and not spam.
Okay.
You're trying to predict a categorical label for each email.
So classification is about predicting category or labels for data points.
Right.
Got it.
Now imagine you're trying to predict the temperature for tomorrow.
Right.
You're trying to predict a continuous value, not just a category.
Okay.
That's regression.
So regression is about predicting continuous numerical value.
Exactly.
Got it.
And Burkov gives a really cool example to illustrate these concepts.
Okay.
He talks about using machine learning to predict customer churn.
Okay.
Which is basically figuring out which customers are likely to cancel their subscriptions.
That's a really practical example.
It is.
So how would we approach that problem using machine learning?
Well, first we'd gather data about our customers, like their demographics, usage patterns, and any feedback they've given. Then we'd label each customer as either churned or not churned, based on whether they canceled their subscription.
So we're starting with labeled data.
Right.
Which makes it a supervised learning problem.
Right. Then we'd choose an appropriate algorithm, like logistic regression for classification. Or linear regression for regression, depending on how we want to predict churn. We'd train the algorithm on our labeled data and then use it to predict the churn risk for new customers.
That's incredible.
It is.
So machine learning can be used to proactively identify customers who are at risk of churning.
Exact.
And potentially take steps to retain them.
Precisely. Now, to understand supervised learning in action, Burkov dives into the classic example of spam detection in Chapter 3.3.
Spam detection. We've all been there.
Yeah.
Battling those annoying emails.
Definitely.
How does machine learning actually help with that?
So think of it like this. We feed the algorithm a bunch of emails that are already labeled as spam or not spam. This labeled data is crucial because it allows the algorithm to learn the patterns that distinguish spam from legitimate emails.
So it's like giving the algorithm a set of examples to learn from.
Precisely.
Just like we talked about earlier.
And one common technique for transforming those emails into something the algorithm can understand is called bag of words.
Bag of words. Okay, that sounds interesting.
Yeah.
Can you explain how that works?
Imagine taking all the words in an email and throwing them into a bag.
Okay.
You don't care about the order, just which words are present.
Okay.
And you compare this bag to a dictionary of all possible words.
Right.
If a word from the email exists in the dictionary, you mark it as a 1.
Okay.
If not, it's a 0.
So each email becomes this long string of 1s and 0s, indicating which words from the dictionary are present.
Exactly.
It's like a fingerprint for each email.
That's it. This string of ones and ers becomes a feature vector that the algorithm can analyze.
I see.
But we're not done yet.
Okay.
The labels themselves, spam and not spam, also need to be converted into numbers. For algorithms like support vector machines or SVMs.
SVMs, those sound familiar.
Yeah.
Can you remind us what they are?
SVMs are a powerful type of algorithm that tries to find the best boundary to separate different classes of data. In the case of spam detection, they try to find the best line or hyperplane in higher dimensions to separate spam emails from non-spam emails.
Got it.
And they require the labels to be converted to numerical values. Like +1 for spam and -1 for not spam.
So we've got our emails transformed into numerical feature vectors and our labels converted into +1 and -1.
Exactly.
What happens next?
That's where the real learning begins. Chapter 3.4 delves into linear models, specifically focusing on SVMs and how they create decision boundaries.
Decision boundaries. Can you elaborate on what those are?
Imagine plotting all those spam and non-spam emails as points in space. With each point representing an email. The SVM algorithm tries to draw a line. Or a hyperplane in higher dimensions. That separates the spam points from the non-spam points. This line is our decision boundary.
So anything on one side of the line is classified as spam. And anything on the other side is not spam.
Exactly.
Pretty intuitive.
But SVMs don't just draw any line. They try to find the line that maximizes the margin. Yeah, the space between the two groups of points.
Between the spam and non-spam points.
Exactly. A larger margin generally means the model will be better at classifying new unseen emails.
Because it creates more robust separation between the categories.
Exactly. It's all about making sure that decision boundary is as clear as possible.
That makes a lot of sense. So maximizing that margin is how SVMs learn to effectively separate spam from legitimate emails.
Exactly.
But are SVMs limited to just straight lines as decision boundaries?
That's where it gets even more interesting. SVMs can incorporate something called kernels, which allow us to create decision boundaries that aren't just straight lines.
So we can have curvy or squiggly decision boundaries.
Yes.
When would we need that?
When the spam and non-spam points aren't neatly separable by a straight line. Kernels are great for handling more complex patterns in the data, allowing us to create nonlinear decision boundaries that better fit the data.
That's pretty powerful. But I'm already sensing that choosing the right kernel might involve some trial and error.
You're right.
This is all starting to make sense.
Good.
But before we get too deep into SVMs, I want to touch upon something we discussed earlier. Overfitting. Chapter 3.5 delves into this common problem in machine learning.
Overfitting is when our model becomes too focused on the training data and doesn't generalize well to new data. It's like memorizing the answers for a test instead of actually understanding the material.
So a model that overfits is like a student who crams for a test.
Exactly.
But can't apply the knowledge to real-world problems.
Right.
How do we avoid this trap?
One way is to use simpler models, like linear regression, which are less prone to overfitting because they try to find a simple straight line that captures the general trend of the data, rather than getting bogged down in every little detail.
Simplicity is key.
Yeah.
And the book explains why squared error loss is a popular choice for measuring the accuracy of linear regression models.
Yeah, it's about finding a sweet spot between historical context and mathematical convenience.
Got it.
Squared error loss is a smooth differentiable function, which makes it easier to work with when using optimization techniques.
Optimization techniques. Are we about to dive into a whole new level of mathematical complexity?
Not quite yet.
Okay.
But Chapter 3.6 takes us from linear regression to logistic regression, which is specifically designed for those binary classification problems we talked about earlier.
Binary classification, like our spam detection example.
Exactly.
Where we're predicting one of two categories, spam or not spam. What's so special about logistic regression?
Logistic regression is all about predicting probabilities. It uses a special function called the sigmoid function to transform linear combinations of features into values between 0 and 1, which represent the probability of belonging to a certain class.
So instead of just outputting spam or not spam, logistic regression gives us a percentage. Like 80% chance of spam.
Exactly.
That's pretty useful.
It is.
But how does it figure out those probabilities?
That's where the maximum likelihood principle comes into play. The algorithm tries to find the parameters that maximize the likelihood of observing the training data.
So it's like saying, given these emails and their labels, what parameters make the most sense?
Exactly.
So it's finding the best fit between the model and the data.
Yeah, just like with linear regression.
It's just like with linear regression, but
instead of minimizing the squared error, we're maximizing the likelihood. It's a subtle but important difference.
This is all fascinating.
Yeah.
But I'm starting to crave a more visual way to understand these classification models.
You're in luck. Chapter 3.7 introduces decision trees. A much more visual and intuitive way to classify data.
Decision trees. I've heard of those.
Yeah.
Are they literally like trees with branches and leaves?
Yes. Imagine a tree where each branch represents a decision based on a certain feature. You start at the top, and each decision leads you further down the tree until you reach a leaf, which represents the final classification.
I can picture it.
Good.
But how does the tree actually grow?
So the book walks through the ID3 algorithm, which uses a concept called entropy to choose the best features for splitting the data.
Entropy, isn't that something to do with physics?
It is. But in decision trees, entropy is used to measure the impurity of a set of data. The algorithm tries to find splits that create the purest subsets, where all the examples have the same label.
So it's like sorting laundry.
Yeah.
You want to separate whites and colors to create the purest piles?
That's a great analogy. The goal is to create branches that lead to leaves where all the examples belong to the same category.
Like all spam or all non-spam.
Exactly.
Makes sense. But decision trees have their limitations, right?
So of course.
Okay.
ID3 in particular can sometimes create trees that are too specific to the training data, which leads to overfitting.
Right.
The book mentions techniques like backtracking, which can help improve the model by exploring different paths in the tree.
Backtracking, is that like taking a step back?
Exactly.
And trying a different branch?
It's all about finding the best tree structure that generalizes well to new data.
This is all so much more intuitive than I expected.
Good.
But Chapter 3.8 takes us back to SVMs. And explores scenarios where linear models might not be the bad choice.
Right. Sometimes a straight line.
Yeah.
Even with a kernel, just won't cut it. Linear models struggle when the data is noisy. Meaning there are outliers or errors in the labels. They also fail when the data is inherently nonlinear. Meaning a straight line can't effectively separate the categories.
I can see how those situations would be tricky.
Yeah.
How do SVMs handle noisy data?
That's where the hinge loss function comes in. It allows the algorithm to tolerate some misclassifications, making it more robust to noise.
So it's like giving the model a bit of wiggle room.
Exactly. It doesn't have to be perfect. Just good enough to capture the general patterns.
I see.
The book also introduces a hyperparameter called C.
Hyperparameter, another new term?
Hyperparameters are basically settings that you, as the data scientist, get to choose before training the model. They influence how the algorithm learns, and finding the right values is crucial for getting good results.
Got it. So C controls how much the model focuses on avoiding errors.
Exactly.
What about nonlinear data?
That's where the kernel trick comes into play. It allows SVMs to transform the data into a higher dimensional space.
Higher dimensional space. That sounds a bit mind-bending.
Think of it like this. Imagine you have a bunch of points scattered on a piece of paper. And you can't draw a straight line to separate them. But what if you could fold that paper in a clever way so that the points suddenly become separable?
So by folding the paper, we're essentially adding a third dimension.
Exactly.
That makes it possible to separate the points with a straight line.
The kernel trick is like finding that clever fold mathematically.
I see.
It allows SVMs to create those curvy, non-linear decision boundaries we talked about earlier, but without actually having to calculate in higher dimensions.
That's incredibly clever. But I imagine there are different folding techniques, right?
You're right. There are different types of kernels, each with its own way of transforming the data. Popular choices include RBF and polynomial kernels. Choosing the right one can significantly influence the model's performance.
It's like having a toolbox full of folding techniques.
Yeah.
And you have to choose the right one for the job.
Exactly. But before we get carried away with the power of SVMs, let's circle back to instance-based learning and delve deeper into the k-nearest neighbors algorithm, or KNN, in Chapter 3.9.
KNN. That's the one that finds the neighbors to make predictions, right?
KNN is all about finding the most similar examples in the training data to make predictions for new data. It's a lazy learner because it doesn't actually build a model, but just stores all the training examples in its memory.
So it's like having a giant library of examples.
Precisely.
And KNN just looks up the most similar ones when it needs to make a prediction.
But the way it measures similarity is important. The book discusses different distance metrics, like Euclidean distance and cosine similarity.
Euclidean distance. That rings a bell from geometry class.
That's right. It's about measuring the straight line distance between 2 points. And cosine similarity measures the angle between two vectors, which can be more appropriate for certain types of data.
So choosing the right distance metric can impact how KNN finds those nearest neighbors and ultimately affect the accuracy of its predictions.
Different metrics, different neighbors, different results.
Got it. But we also have to decide how many neighbors to consider, right?
Absolutely. The value of K
K and KNN
is another important hyperparameter that we, as data scientists, need to choose. A smaller K means the model is more sensitive to noise and might overfit, while a larger K can make it too smooth and underfit.
Finding that sweet spot for K is crucial. It's like Goldilocks trying to find the porridge that's just right.
Yeah, great analogy.
Not too hot, not too cold.
Exactly. But this all seems a bit disconnected from those optimization techniques you were discussing earlier. How does KNN fit into that picture? It doesn't actually rely on traditional optimization techniques. Like gradient descent, which we'll delve into later. Instead, KNN focuses on finding the most similar examples and using them for prediction. It's a more direct approach to learning from data.
Fascinating. So KNN offers a different perspective on learning.
Exactly.
Compared to those model-based approaches we've been discussing.
Now that we've explored some key algorithms for both classification and regression, let's dive into the world of optimization. Chapter 4 introduces gradient descent, a core algorithm used in many machine learning models.
Gradient descent, that's the one where we imagine ourselves descending a hill, right?
Yeah, I got it. Imagine you're standing on a hillside and want to find the lowest point. Gradient descent is like taking small steps downhill, following the steepest slope until you reach the valley.
So it's like navigating a mountainous landscape to find the optimal solution.
In machine learning, that hillside is represented by a cost function, which measures how much error our model is making. And that lowest point represents the optimal parameters for our model, the ones that minimize the error.
So gradient descent helps us fine-tune those parameters to make our model as accurate as possible.
Precisely. Burkov explains how the algorithm works.
Okay.
Using linear regression as an example.
Okay.
It shows how the parameters are updated iteratively,
okay,
step by step, to gradually reduce that cost function.
Yeah.
And improve the model's accuracy.
Iteratively, meaning it keeps taking those small steps downhill until it finds the best solution.
Exactly.
But how big are those steps? And how do we know which direction to take?
That's where the learning rate comes in, which is another hyperparameter that we get to control.
Okay.
It determines the size of those steps.
Okay.
A learning rate that's too small can make the algorithm slow, while a learning rate that's too large can cause it to overshoot the optimal solution and bounce around.
So just like with K and KNN, we need to find that just right learning rate for gradient descent. It's like Goldilocks is back to help us find the optimal settings for our algorithms.
Exactly. But choosing the right learning rate is just one piece of the puzzle.
Okay.
Chapter 4.2 dives into different variations of gradient descent.
Variations?
Yeah.
Tell us more.
One popular variation is stochastic gradient descent.
Okay.
Or SGD.
Okay.
It's like taking smaller, more frequent steps downhill, which can be faster than traditional gradient descent, especially for large data sets.
So instead of using the entire data set for each step, SGD just uses a small sample.
Exactly. And the book also introduces techniques like adagred and momentum, which further improve the convergence of gradient descent by adapting the learning rate and smoothing out the steps.
So they're like giving our algorithm a boost of energy and a better sense of direction to help it reach the optimal solution faster.
Right.
This is all starting to sound very sophisticated.
It is.
But before we delve into the realm of neural networks, let's shift our focus to the more practical aspects of working with machine learning models.
Sounds good.
Chapter 5 is all about putting these concepts into practice.
Right, the practical side of things.
Practical aspects. I'm guessing this is where things get less theoretical and more hands-on.
Exactly.
What kind of practical challenges do we need to be aware of?
One major challenge is feature engineering, which is all about finding the best way to represent our data for a specific learning task. Remember how we transformed those emails into numerical feature vectors? Using the bag of words technique? That's feature engineering in action.
So it's not just about converting everything into numbers, but about choosing the right features.
Exactly.
And representing them in a way that helps our algorithms learn effectively.
Precisely. The book provides examples of other feature engineering techniques. Like one-hot encoding for categorical features, binning for numerical features. And normalization and standardization for scaling features.
That's a lot of techniques.
It is,
Can we break them down one by one?
Sure.
Let's start with one-hot encoding. What's that all about?
One-hot encoding is about converting categorical features, like colors or days of the week, into multiple binary features. So instead of having one feature called color, with values like red, green, and blue, we'd have three separate features. Is red, is green, and is blue, each with a value of 0 or 1.
So it's a way to represent categorical data in a way that algorithms can easily understand.
Exactly.
What about binning?
Binning is about grouping numerical values into ranges or bins. For example, instead of using a person's exact age, you could group them into age ranges like 1825, 2635, and so on.
So it's a way to simplify numerical data.
And
potentially make it more meaningful for certain problems.
Precisely. And then we have normalization and standardization, which are both about scaling features. So they have similar ranges. This can help improve the performance of many learning algorithms.
So it's like making sure all the ingredients in a recipe are in the right proportions.
That's a great analogy.
But sometimes we encounter missing data. Those pesky blank spaces in our data sets. How do we handle those?
The book discusses different imputation techniques for handling missing data. One common approach is to replace missing values with the average value for that feature.
So if we're missing someone's age, we can just fill it in with the average age of everyone else.
That's one option. Another is to replace missing values with a value outside the normal range, signaling to the algorithm that something is missing.
Clever. I imagine choosing the right imputation technique. Depends on the specific data set and the problem.
Absolutely. There's no one-size-fits-all solution.
But after we've engineered our features and handled missing data, How do we actually choose the right learning algorithm for the task?
Yeah, that's a great question.
There are so many options.
There are.
Chapter 5.2 provides a framework for algorithm selection.
Yeah.
Highlighting factors like explainability, dataset size, feature types, nonlinearity, training,